Okay. Okay, so today, welcome to the stream. No music. I'm gonna keep it very short. Okay, so today, why is my thing going? Okay, so today, what we're gonna do is we're gonna go over this code, which is actually an implementation of a very basic GPU on Verilog. So let's actually take a look at the repo over here. Okay, so this is the GitHub repo I'm referring to. So I'm gonna go to my repositories recently. So we're gonna implement a minimal GPU design in Verilog to learn how GPUs work from the ground up. So um, so I'm assuming that you already know how a CPU works, at least the gist of it. So there are like basically 5 stages: fetching the instruction, decoding the instruction, executing the instruction, and then writing it back to memory. Well, that's just the same thing in a GPU, but GPUs leverage something called, let me get, so GPUs leverage something called SIMD, and what SIMD stands for is similar instruction but multiple data. So these are the kind of stuff that these are the instructions. Let's say a for loop. So let's say you have a for loop of variables doing the same thing. So you have a addition in loop. This can be seen in like arrays. Like in a loop, you're updating an array, and each update is actually independent of each other. So in those kind of cases, you're gonna have this kind of SIMD instruction which can be executed in parallel, and that's what the GPU is good at, right? So keep in mind that the author says that Tiny GPU is a minimal GPU implementation optimized for learning about how GPUs work from the ground up. So the project is gonna mainly focus on 3 things: architecture, parallelization, and memory. Okay, so let's take a look at the architecture. The first thing we have here is the GPU itself. So the GPU, well, what it does is a GPU executes a program called a kernel. Now, what is a kernel? A kernel is something, you can just call it a piece of program or a set of instructions. Um, so an example of a kernel provided in this repository is, it should be over here. Okay, let me just pull up this. And okay, so here we're gonna have our assembly codes. Yep. Okay, so here is you can call this a kernel. Okay. We have, let's go to a simple example where we are adding two 1x8 matrices. So we're performing 8 element wise addition in separate threads parallelly. So what we're trying to do is we're trying to do all of these things parallelly. So as I said, this right? Yep. So what's gonna happen here is this is our program counter. We get the PC value from here, okay, and this is all the stuff that's gonna happen. So you have these register files which give you the data, okay, rs and rt, the source and other register. So this is where the data comes. You have your arithmetic unit, and you have the memory unit, and finally the a mux which takes care of stuff. So you can write back data here through rd. Rs is the source register. This is the other, I think, the ternary register, I don't know what you call it, but these are the two registers which you take input from, and rd is a register which is the destination register. You write it back there, and that's what happens here. So this is basically the execution unit you find in any CPU, so it need not be a GPU as well. So the main advantage here is that so you identify these set of instructions, right? So what you do is you set a number of you try to start parallelizing this. So how does it start is you load the global program with the kernel code, you load the required memory, so you have program memory and data memory, so you load those first. Then what you do is specify the number of threads to launch in the device control register. So all this device control register is doing is like a top down flow here, the GPU. So all the device control register is doing is that it keeps the track of the number of threads. So what happens is when you keep track of the number of threads, what it does is it just holds that info for the dispatcher, so that the dispatcher can look at the number of threads and organize them into groups that can be executed parallelly. So threads, in the sense, these are basically programs, right? So you do that. So the dispatcher gets all of these threads, and then the dispatcher organizes these so-called threads. It groups threads into blocks, right? So yep, so you see the device control register just stores a thread count. Okay, now once a kernel is launched, the dispatcher is the unit that actually manages this distribution of threads to different compute cores. So this is a compute core here. So you have one compute core. So what happens is the scheduler is over here. What the scheduler does is it just executes in so what it ensures is that well, before each compute core processes one block at a time. So what the dispatcher does is it creates these threads into a number of blocks, and each block is sent to a compute core, where each compute core computes one block at a time. So you can have two compute cores and do two blocks at a time parallelly. So that's up to you how many cores you want to specify. So that is a job of the scheduler. Now let's actually just take a look at the code to understand what's happening. So the first thing we talked about was the device control register. So this is written in verilog, and we can see that it takes in the main inputs. It takes in are the right enable, so you can just store how many threads. So this is signal to enable the write. So this is the device control data, which is actually the input of the thread count you are giving, and this is a thread count output which is passed on to the dispatcher. So that's what is happening here. So on the positive edge of the clock, we check that if you want to reset this device control register, you set the number of threads to 0, okay. And we have this sorry, before I jump to a conclusion, we have a register here which stores the value. So it's like a wire coming in, um, it's like a wire coming in, and there's a register here, and then this is the output. So that's how it's gonna look like. So on the positive edge of the clock, we set the value of this register to 0. Else what we do is we set the value of the left hand side of the register onto the and transfer it over to the wire on the right, so it's a continuous assign. So that's what happens. That's it. Now what we do is we move on to the dispatcher. So this dispatcher actually receives the thread count, okay, and it also has to communicate between the cores, so that it sends it ensures that a core is processing one block at a time. So that's what is happening here. So dispatcher is also useful for grouping the threads together into blocks. So the logic for grouping threads together into blocks is actually pretty simple. What you do is you actually you just ensure that there are enough blocks for each thread. So let's say I have 11 threads, so I would need a total of at least 3 blocks to do it. So this is actually the statement that does that. So it just this statement is equivalent to the ceiling of thread count over threads per block. So it ensures that any block with less than the specified maximum threads per block, they are still counted and can be processed. Okay, so apart from that, we also need to keep track of how many blocks were dispatched and how many blocks were done. So if the number of blocks that are done is equal to the number of blocks that were dispatched, then that means you are done processing for that specific core, right? Okay, so what we do is for each core we keep track of the state. So there's core done, there's a core start, there's a core reset. So for each core we keep track of these flags, and notice that this core done signal comes from the core, so it is an input to the dispatcher, and the remaining are actually outputs. So the dispatcher controls when a core starts, when a core resets, and also it computes the core block ID. So this block ID is actually useful uh, in getting the address of the data required for that core to perform computation on, and also it keeps track of the core thread count, so that we'll see why this is important in a while. So for each core it keeps the thread count. So we'll check how that is handled. Like, so this is basically important to know whether a block has been done or not. So okay, so inside this huge always statement, we basically have like 4 main parts, let's say. Okay, so if you issue the reset signal, we basically zero out all these signals. But what we do, we zero out all these signals except for the core reset signal, which we set to 1, and all of these happen using non-blocking statements. So all of these are actually done in parallel. And okay, else if you are ready to start dispatching the blocks, what you do is you can ignore this here. This is just a workaround because you're already using a clock here inside an always block, so you would need to like latch the start signal so you don't depend on 2 clocks. But this is just unimportant hack, let's say. This is just a functional thing that makes it function because of how EDA software simulated. Okay, you can ignore this part, but what's the main thing is, well, the basic condition is if the blocks done equal to the total number of blocks, that means you are done processing all the blocks, and the dispatcher can assign done to be 1. That's the output. So that means your entire program has been all your blocks have been processed, right? Your kernel is finished executing. Okay, now what you do for each core is that you check if a core has been reset. Okay, first that's your priority, to check if a core has been reset. And if the core has been reset and there are more blocks to be dispatched, what you do is so basically, when do you reset a core? You reset a core when you're done with a block, right? So if a core has reset, you just check if there are more blocks to be dispatched. So if blocks less dispatched is less than total blocks, you start that specific core, and then you assign the core block ID, which is actually just the number of blocks dispatched. So for the first block that comes in the first core that receives the core block ID for the first core will be 0, and then for the next block that comes this second core, which is core 1, if the first block was core 0 and the second block is core 1, core 1 is going to get the blocks dispatched of value 1. So that's it. That's not pretty, no complications there. Okay, so this and now what you do is you also assign you also check the number of threads you have, right? So each core can handle some number of threads. So now threads in this case are actually just SIMD kind of instructions, where SIMD stands for similar instruction but multiple data, right? Okay, so that's your core thread count. So you check that if you're processing the last block, then you're gonna assign only how many ever threads are remaining. So otherwise it's you know that if it's not the last block, it's definitely filled with the maximum threads per block, because that's how we design our total blocks. So you just do this assignment here, and you increment this blocks dispatched variable, because now you have actually started a core and assigned dispatched a block to that core. Okay, now if a core has just finished executing its current block, we are going to reset it, and then this loop is going to happen again and followed by this. So that's how the dispatcher controls the cores and the blocks, right? Now once we get into the compute core, we'll actually understand why we need this thread count, right? Okay, so here we have defined the default number of cores to 2 and 4 threads per block. Okay, now going back to the repository, right? Okay, so now what happens inside a compute core is we have a scheduler. Now a scheduler is something that you can go here. Okay, let's search for scheduler. There's scheduler. Each core has a single scheduler that manages the execution of threads. The tiny GPU scheduler executes instructions for a single block to completion before picking up a new block, and it executes instructions for all threads in sync and sequentially. Okay, so basically the author is saying that you execute instructions for a single block. Okay, so it executes instructions for all threads in sync and sequentially. Okay, now you might be confused. I just said that this is parallel, but now the word sequentially pops up. So what this basically means is that a compute core, let's look at the expanded view for compute core here. This is a compute core. So the scheduler basically ensures that you do one block at a time. Okay, so you get the threads, you get the instructions, you fetch the instructions, you decode the instructions, and set the decoder basically sets the control signals, telling which ALU operation to perform, which memory operation to perform, and how to get the program counter and all that. So that's what the decoder is. Now basically what happens is you see that each compute core can actually have 4 of these units together. So what is happening is that let's say I receive one block for this compute core to process, and it needs to process 4 threads. So each of the thread is gonna have go to all of these 4 units, one thread in this, one thread in this, one thread in this, and one in this. So what's gonna happen is that they're gonna be executed in sync. So all of these are going to be executed in sync, and only when all of them have finished their output, where the compute core is going to say that it's done processing a block. So let's say thread 1, 2 and 3 are done processing, but thread 4 is still processing, then we won't send a done signal back to the dispatcher. So we will only send a done signal when all of the threads are done processing, to ensure that the data is legit. So that's what that's what happens in the compute core. But let's look at the code as well. So now we are moving on to the scheduler. So the scheduler manages the entire control flow of a single compute core. So it fetches the instruction from program counter, and then it decodes the instruction into relevant control signals. And then if you have an instruction that accesses memory, so we trigger the async memory request from these LSUs. Now what we do is, when we wait for the memory to come, and then we proceed to the execute phase. So the data is fetched from the memory onto the local registers, and then we are ready to do operations. Now once the operations are done, we update the register values from this program counter, and then later you can have a memory write back stage which is going to the LSU again. Or I don't think it goes to the LSU, but you do send it back to the memory controller, and there where the updated values are stored. So each core has its own scheduler, where multiple threads can be processed with the same control flow at once. So as I said, 4 threads at once can be done, but this has to be done in sync. So technically different instructions can branch to different PCs, requiring branch divergence. So in this thing, so the thing is, you can have a jump statement inside a for loop, right? You can have an if statement, you can have all these branching conditions that might go to a different program counter value. So we're not gonna deal with them here in this minimal implementation. It has assumed no branch divergence. So to keep things simple and explainable, that's what we're doing here. Now, okay, let's look at the fields of the scheduler. We have the basic control signals, clock, reset and start. Then we have decoded. So basically this is the decoded memory. So we have the read enable, write enable, and the return value. And then we have our memory access state. So this is the fetcher state, this is the LSU state, this is the current PC, and this is the next PC. Okay, now here we also have our execution state. So this is basically so yeah, okay, yeah, this is our core state. So you can actually see core state actually keeps the count of the threads that have been processed. So if the core state, we're gonna have like, wait, yeah, so if a thread, sorry, yeah, we're gonna have a core state, and we're gonna define our core states here, which are going to be basically these 6 states: fetch, decode, request, wait, execute, and update. So each core has its own scheduler, right? So that's what we do. So what happens in this is, it's going to be a more to intake, but Well, what we do is on a reset, we set the program counter to 0, we set the core state to idle, idle being the 0 state, right? So you can say that this is a core state where that happens just after resetting a core. So there we do that idle and we set done to 0. Else, so if we're in the idle state, what we do is we go to the fetch state, right? So here it's written after reset, before kernel is launched, or after previous block has been processed. So that we saw in the dispatcher over there. We're going to start by fetching the next instruction for this block based on the program counter. So we're going to go to the fetch state and we're going to assume that the program counter is actually ready. So we move on to the fetch state. Okay, so now if we're going to assume that once you're in the fetch state, the compute unit is gonna fetch the required instruction, and then we're gonna move on to the decode state. Now decode state is gonna move to the request state for one cycle, and we're gonna assume that all of this happens in enough time that it requires only one cycle. So request state, once we're done requesting, we're gonna move to the wait state. Okay, now here is where the memory controller comes into play. We wait for all of the memory controllers or LSUs to say that the data is ready. So if we look at the LSU here, this is the load store unit. So it's gonna have these statuses. So it's status of 00 means idle, status of 001 means requesting, status of 10 means waiting, and 11 means done. Now what happens is we check if no LSU is requesting or waiting, because it's fine to read data when the LSU is idle or it's done. So if any LSU is in the state, we keep waiting. So we keep waiting in the state. So if no LSU is like waiting, so that means that if any LSU waiting is actually 0, that means all LSU are in either idle or ready. We can move on to the next stage, which is execution. That means we have our data ready. Now we're going to execute our thing, and we're going to assume all this happens in one clock cycle, and we're going to move on to the update stage, right? Now in the update stage, this is where we write back the value to the resultant register. So if we reach a return instruction, then the block is done executing. Okay, else we assign the current PC to the next PC. Okay, so we have our next PC stored for every thread, right? So that's what we do here. We assign the next PC over here, which is actually an input here. So the next PC updates every clock cycle to this scheduler unit. So we assign the current PC to the next PC, and then what happens is this update is synchronous, so we move on after one cycle. So we don't go back to the idle stage, right? So we go back to the fetch stage. Okay, now what happens, like if we reach a return instruction, only then we move to the done stage. And then what happens is in the done stage, since the flag is already set to 1, there's nothing else to be done here. We just wait for us to go back into the idle stage, where the dispatcher tells the code, where here we send to the dispatcher that we are done processing this block, send me another block. So we go to this done stage, where there's one cycle of this done is going to stay high for this, and during this cycle in which the dispatcher is gonna see that and send a reset signal. So that's about the scheduler and this decoder. I mean, we didn't talk much about the fetcher and decoder, but let's check. Um, Now, one thing that we have to check here after the scheduler is I feel we should go on to the fetcher. So the fetcher actually deals with the program counter. So let's go check that, and it also deals with the program memory. So we go to fetcher. So the fetcher basically retrieves the instruction at the current PC from global data memory. Okay. Now each core has its own fetcher. So okay, so let's look at this fetcher here. So actually, before we move on to the fetcher, I feel like it's important to have an idea about the memory controller. So the tiny GPU data memory has the following specifications: 8-bit addressability, that means we have 256 rows of data memory, each storing 8-bit data. And the program memory is also the same depth, 256 rows, but each row stores 16-bit data. So that's what we're gonna look at. Oh, I'm just checking my avatar. Okay, now that's what we're gonna deal with. So right, so global memory has fixed read/write bandwidth, but there may be far more incoming requests across all cores to access data from memory than the external memory is actually able to handle. Yes, that's true, because and that's kind of the main bottleneck, I guess. You're reading data faster than um, it's available, right? So the memory controllers keep track of all the outgoing requests to memory from the compute cores, and then they throttle these requests based on the actual external memory bandwidth and relay the responses from external memory back to the proper resources. So you can also see that there are multiple channels of data requests coming into the memory controller. The memory controller has to respond to all of these channels based on the global external memory bandwidth. So each memory controller has a fixed number of channels based on the bandwidth of global memory. So you kind of have a ratio, right? Say you might have these warnings. So you get some warnings saying that your phone internal speed is capable of 6 Gbps, but your cable only supports 3 Gbps, or so on, or your memory controller only supports 3 Gbps. So this is like a common bottleneck that is a people face. Okay, so now that we've talked about the controller, let's look at the code for the controller. The memory controller receives the memory requests from all the cores. It throttles the request based on limited external memory bandwidth, waits for responses from external memory, and distributes them back to the cores. Okay, so now what this controller does is, we're going to define our address bits 18, data bits as 16, and we're going to say that we have 4 consumers. So at a given time you can have like a maximum of 4 consumers accessing the memory through this controller, and for simplicity's sake we're going to keep it to 1 channel. So the number of concurrent channels available to send requests to global memory. And then we have write enable. So in case you need to update like your DRAM values from the register files, right? But you don't have to do this for program memory. It only happens for data memory. So let's set that to 1 though. Okay, and you have your basic input signals, clock and reset. Okay, so now this is what we're gonna look at here. This is what the compute cores are gonna request. These can be the fetchers, which fetch the program program data, and or it could be the LSUs, which try to get the data that the cores require for computation. Okay, so we're gonna set like 4 signals for each read and write. So we're gonna go through all of them. So we're gonna go through this thing first, which is consumer read valid. So I'm going to just zoom in here and we're going to look at this. So consumer read valid, what does this do is it just tells if that whether the whether you can read this data or not, right? So and this is an input. So this just tells that the data that you have waiting at the input, like the address over here, okay, the address that you're going to read, is it actually valid? So if it's valid, you're going to send this read address here. That's what we're going to that's what the memory controller is going to look up in the memory. And then once the data is ready, you're going to have this signal that you send here, after which you can actually read the data through this read data port, right? So you can see that it is data bits wide and depends upon the number of consumers, which is actually 4 here. So since we have 4 units in a compute core, that's why we're gonna assign this to that. So that's what we're gonna do. And the memory thing, it's gonna serve one compute core at a time, and each compute core has 4 of those things inside. So that's why we choose this convention over here. So okay, now the same for the write. So in the write, if you want to write some data, you have to tell if it's valid or not, and the address you want to write to, the data you want to write to. Notice that these 3 are input in this case, and this was output here, but this is an input here. The write data is sent here, and once the write is actually ready to be done, you actually send this write ready signal, and then you just hope that the memory controller updates the value in the DRAM. So that was about the consumer interface for the fetches or LSUs. Now this is for the data or program. So okay, so what you're gonna have here is the same thing. You're gonna have these 8 lines of code, but this is just for the data or program. So this is about mem read valid, mem read address, mem read ready, mem read data, so on. So you can say that this is the inputs. Okay, these are the consumer side of stuff, and this what happens between the memory and the controller. So you have an output register, which is number of channels minus 1. So you're gonna handle 1. So it just tells if the read data is actually valid or not. Okay, so now what happens is you're gonna have a read address. Okay, for each channel you're gonna have a read address, right? And then for each channel you're gonna save the, if you're ready to read, so for each channel you're gonna check if the address is valid, and then for each channel, once the data is ready, you're gonna send this signal over here for each channel, and then each channel has its the data it read from the memory. And now of course each channel is going to have the same thing for the write data. Each channel could have some write valid signal, and the data it wants to write, the address it wants to write the data to, and then whether it's ready to write or not, right? So this actually very similar, but we just segmented these because we want to differentiate between the fetcher and LSUs and the data or program. Okay, so now we're gonna go into this code block over here. So okay, on reset we just zero out all of the signals, because that's what we're gonna do, right? So what we're gonna do is now we're gonna try to um, handle all of the channels one by one. So we're gonna start with channel number 0 until the last channel number, in this case, which is 1 only. So this loop is actually kind of pointless here, but you can see uh, when we try to increase the number of channels, this is actually a good programming practice. So okay, so first we're gonna define a controller state. So we saw that there are like 5 states for the 5 states for the controller, if I'm not mistaken. Yeah, for 5 states. So it can be idle, read waiting, write waiting, read relaying, and write relaying. So okay, so while we're in the idle state, okay, we're gonna check all the channels, right? So if this channel is idle, we're gonna cycle through the consumers looking, and we're gonna look for the consumer with a pending request, right? So we're gonna look for the consumer with a pending request. So how do we check that? So we have these consumers here, right? So whoever are actually looking for a pending request, they're not gonna have their ready signal high, right? So we're gonna look for the consumers that okay, so we're gonna keep track of the channel serving customer, right? So we have that here. Okay, we missed this part here, so let's go through it. Okay, we're gonna have a controller state here, and then we're gonna check which current which consumer is each channel currently serving. Okay, so if we do current consumer of 0, that means whatever is in current consumer of 0, that means channel 0 is serving that consumer. So now which channels are being served? So we check. So what this does is that it prevents many workers from picking up the same request. So that's why we check here that if this channel is not serving this customer and the customer's read is valid, okay, and we're not serving this customer, then we're gonna start serving this customer, okay, and we're gonna set the current consumer, right? We're gonna set the current consumer of this channel to be J, right? So we're gonna say that this channel is busy. Yes, it is busy serving customer J, right? So basically channel serving customer J is 1, and this channel serving customer is actually yeah, it's a thing with number of consumer. I keep saying customer, please ignore that. So it's number of consumers. So it basically tells if that this consumer, does it have a channel serving it or not. That's it. And then this variable actually tells us that which channel is serving which customer. So the current consumer in the ith channel is J, and this jth consumer is someone who has a pending request. Okay, that's all that's happening. And now what we're gonna do is now since the consumer's read is valid, what we're gonna do is we're gonna move on to the memory interface here, and we're gonna say mem read valid, right? We're gonna assert this, okay, and then we're gonna copy over the address of the consumer into the mem read address over here, okay, and then we're gonna say that we are waiting for a read. So that's what we're gonna do. Okay, we move on to the read waiting. Okay, so let's say else, so if this consumer if this consumer wants to write, so here we were checking a read, so we do reads before writes first. So what happens is we check if the write if the consumer wants to write and we're not serving this customer. So we're gonna say that okay, this consumer is actually being served by a channel, so we're gonna mark that, and so that we don't assign another channel to that consumer. So and we're gonna say that this um, channel I is serving consumer J. Okay, so now what we're gonna do is we'll issue since we have only one memory interface and multiple people, we actually need to keep this separate. So that's why we're just gonna copy over the consumer write valid signal to the mem write valid, and the same for the other signals. And instead of moving to the read waiting stage, we're gonna move on to the write waiting stage. Okay, so we have defined two possible ways of execution right now from idle, and that is either going to read waiting or write waiting. So let's take a look at read waiting. So we're just gonna basically query the memory here and wait for the response. So um, what we're gonna do is once the memory is actually ready, right, we're gonna copy the we're gonna copy the data from the memory read to the consumer read, and we're also gonna say that the consumer read is ready, and then we're gonna set the controller state to read relaying. So now we're gonna wait until the consumer acknowledges that it received a response. So you can see that this is an input over here. So we're gonna say consumer okay, read relaying, right? So what we do is we check if the consumer read is not valid. Okay, that means if the consumer read is not valid right now, so current customer of I, so current consumer of I basically says that it refers to the consumer number which the current channel is serving. So channel I is serving customer J, and that's basically J here. So if the consumer read valid is not is 0, what we're basically saying is that you are done relaying, so we're gonna free the channel. So the we're gonna say that this consumer, no channel is serving this consumer as its request has been done. And then we're gonna say that current consumer I, so this consumer that this channel is serving, the consumer read ready is 0. So we're gonna basically copy this, I mean kind of do the same for the consumer read ready, because this is an output over here. So and the other output is read data. So we already assigned read data, and now we're gonna assign read ready to be 0, because now we are relaying the read, and then we're gonna go back to the idle state. So that's what happens in read waiting. Now we're gonna go to write waiting. A similar stuff happens, but it's just writing data. So so if we are ready, if the memory has written data, we're just gonna copy over, we're gonna put the valid signal to 0. We're gonna copy the data to the, we're gonna say that this thing consumer write ready is 1, and that means and then we're going to move on to write relaying. So now in write relaying, what we're going to see is that if consumer So if consumer write valid is actually 0, what we're gonna do is we're gonna yeah. So if the consumer write valid is 0, I mean we're basically saying that we have acknowledged your request and we're setting it to 0 right now, because so if it's 0, that means this has been accepted here, and so we're saying that no channel is currently serving this consumer, and we're gonna say that for this consumer the write ready is 0 because we have written it, and we're gonna go back to the idle state. So these relaying steps are kind of like the reset signals for the consumer. So what this memory controller is gonna expose is that read ready and read data. So we want to ensure that these things are like high for only for one clock cycle, and we're going to set them back to 0, so that you can distinguish, and when exactly when the data is ready. So that's why we're setting them back to 0 here, and we're setting them back to 0 only when these are 0. So while we don't want to basically relay a write when the consumer write is still valid, right? That's what we're doing here. Wait, that covers the controller. So now what we're gonna do is, now that we have covered the controller, we'll look in the caches later once we implement the core. We'll move on with the core, which has fetcher, decoder, register files, LUs, LSUs, program counter, and finally the instruction set architecture. So I feel like this part can be done later, but we do need to know the instruction set architecture so that so we can design the decoder properly, right, and the decoder and the ALU. But I feel like that the ALU can be done, except the control path we can do the execution part of the ALU, so on. So we'll take a look into how all of this works in the next stream or the next video, and then we'll actually run all of these codes, try to interpret the results, and think about future additions to this repository, because there seems to be some ambitious goals like adding pipelining, adding branching, what else, simple cache. There's no cache yet, so we can add a cache, optimize control flow and use of registers to improve cycle time. So if you want to minimize the use of registers and increase the improve the time efficiency, there's this method called register minimization, which happens in this there's a concept of folding and unfolding. So whenever you unfold and fold architectures, or you add delay blocks, what happens is you can actually reuse certain registers. So that's basically, you just keep track of when a register is needed and not needed, so that you can reuse certain registers. That's it. But what I feel is that once we get all of this working, we will move on to the next part. So we'll be implementing the compute core, so out of which we have already discussed the scheduler, and we have a brief idea of what all of these things do, but we're gonna go into their interaction with the memory controller, and how the ALU passes info to register files. So we're basically gonna work on this thing over here. So we're gonna work on this thread execution unit, and that's basically this unit over here. So each compute core has 4 of these units, and that's what we have to do. So if we go to core.sv, so we're going to see that we have 4 threads per block. So that's exactly what's going to happen here. So each compute core has its fetcher, a decoder, a scheduler, right? And then for all of these 4 threads, we're gonna instantiate an ALU, LSU, a register, and a program counter instance, so that we can update and get the next program for this specific unit. Okay, that's it for the stream. You can go chill or do whatever you want.